Good morning. This next lecture presentation is going to be covering the beginnings of thermochemistry. In this lecture presentation, you can see all the different LOIs that we need for AP Chemistry. However, just to summarize, we're going to be learning about the initial energy concept, looking at how to calculate internal energies, relating it to heat and work, and then finally getting into heat capacities. Let's begin by defining energy. Energy is the capacity to do work or to produce heat. You'll also see it termed as the ability to cause change. So basically, we're trying to get some object to move in order to produce the work. The law of conservation of energy says that energy can be converted from one form to another, but can neither be created or destroyed. It's only simply changing forms. The total energy content of the universe is a constant. Let's first define the main types of kinetic energy that we will see during chemical processes. The first of which is your potential energy, and that is energy that's due to the position or the composition of these substances. The main place where you will see potential energy is during a chemical reaction, so your chemical bonds being broken or created, and your IMFs that are occurring between the different molecules. Main places that you will see this will be your chemical reactions and your phase changes. So when we're looking at the IMFs, remember, to go from a solid to a liquid, liquid to a gas, we need to overcome all those different forces of attraction that are holding the molecules together. That would represent your IMFs. The bond making and breaking, as we look through a chemical reaction, changing over from the reactants to products, those are going to be the bonds that are broken and formed, which is another type of potential energy. When we focus on kinetic energy, that is energy due to the motion of the object, and it depends on the mass of the object and its velocity. The main place where we see the kinetic energies involved in your chemical processes would be heating your substances in these phase diagrams. Heating the substances where you have a change in temperature. So I'm just going to put down here a delta T. So we have a change in the temperature for a system. That is going to be where we see the kinetic energy most often. We could see it again, just depending on the type of problem, with a gas law component, where you could look at some type of process undergoing the ideal gas law and using some energy component with that for part of the reaction. So there are many different ways where you can see it, but typically you're going to see the changes in temperature for whatever it is within a system where we see the kinetic energy most often. So when we look at energy, oftentimes we have to look at both the amount of heat that is absorbed or released from a reaction and the work that it gets done. Work is defined as the amount of force that is applied over a certain distance. By definition, 1 Newton meter, which would be force times distance, is equal to 1 joule, which is our unit of energy. So we can have different forms of energy that are contributing to the overall internal energy for the system. We'll talk about that more coming up. But with the heat, we're talking about the thermal energy, so transferring energy between the two objects due to a temperature difference. Again, heat is always transferring from something hot to something that is cold. So when we look at energy itself as a combination of both the heat and the work, energy is what we define as a state function. Work and heat individually are not. So a state function is defined as some type of property that does not depend in any way on the system's past or future, only depends on the present state. So we'd want to look at the initial and the final positions for a state function. The path that they take to get there is irrelevant. The easiest thing that I can tell you guys to help you kind of figure that out, if you're thinking about, say, leaving my room and going to the cafeteria for lunch, it's pretty obvious. When you leave my classroom, you've got multiple ways, 3 or 4 different ways that you could go to the cafeteria. Your first position, my classroom, and your final position, the cafeteria, are the same, but your path to get there could be influenced by traffic patterns. If there will be a larger amount of people going by the front office, then you might go downstairs and go outside and walk through the courtyard to get to the cafeteria. The path that you take is irrelevant. Your initial and your final positions are what matter. As I was just mentioning, the SI unit for energy is the joule. A joule is defined as 1 kilogram times meter squared per second squared. You have an older non-SI unit that is still widely used, which is the calorie. But like I was saying, you have a number of different types of energies that are out there, but their units always come out to equal 1 kilogram times meter squared per second squared. So just as a reference to that, when we have our force equals mass times acceleration, again, mass is in kilograms, acceleration meters per second squared. So when I take that equation, work equals force times distance, I have this, which is defined as the 1 Newton, kilogram times meters per second squared. So I can take that, kilograms times meters per second squared, and I can multiply that by meters, and you'll notice I get now meters squared. If I look at kinetic energy, KE equals 1/2 m times v squared. So again, kilograms times, and I would have meters per second, but it would be quantity squared. So once more, kilograms times meters squared per second squared. I could have potential energy, where I have mass times gravity times height. Kilograms times the meters per second squared for the gravity times meters for the height. Again, kilograms times meters squared per second squared. So any different form of energy that we have for physics, their energies will always come out to be the equivalent of a joule. So let's now look at a few standard definitions that we will be using throughout chemistry in this unit. The first one is the system, and the system is going to include any molecules that we want to study. In this particular case, we have H2 and O2 being the system, and then we also have the surroundings, which is basically everything else. So when we're talking about the system, you can look at the process or the reaction that is taking place, and by process, if we had a phase change taking place, we could look at the substance that's actually undergoing the phase change, or a chemical reaction. So when we talk about the system, we typically will be looking at a closed system where neither matter nor energy can leave if we have an isolated system, which we try to with our calorimetry experiments. We also can have just a closed system where matter cannot enter or leave, but energy has the ability to leave the system. So when we look at any of these types of reactions, you just have to remember that the heat flow is going to be equal and opposite in direction between the system and the surroundings. Whatever happens to the system, the surroundings is doing the opposite. So when we talk about the surroundings, again, that is basically everything else that would be around it. A lot of times it's, if we're talking about an aqueous solution, it's the water that is present in the solution. If we're talking about a gaseous system, it could just be the walls of the container, any of the lab equipment, thermometers, etc., that would be in there. Measuring temperature changes, that would also be a part of the surroundings as well. Potential energy, which is the energy that is stored in bonds between the atoms, is an energy that an object possesses by virtue of its position or its chemical composition. So when we talk about the position, we can talk about how closely those particles are spaced towards each other. And if we're talking chemical composition, it could be whether or not it's a single bond or a double bond or a triple bond. When we look at the form of potential energy in molecules, its most important is the electrostatic potential energy, which we call E sub EL. And this is basically going to be using the Coulombic forces of attraction and repulsion equation, where we can see the Q1 times Q2 divided by the distance will give us the proportionality for the electrical energies. We've talked about this type of graph before when we were discussing the bonding back in the fall. Again, if I have like charges, they will repel each other. The closer those charges are to each other, the greater the repulsive forces will be. The greater the separation, again, larger distance, you would now have less repulsive forces acting on those objects. And in the bottom of the diagram, you can see where I have the oppositely charged particles. Now, the greater the separation between the molecules, the less attractive those forces are acting on each other, but the smaller the separation, the greater the attractive forces. So remember, when we're talking about our bonds, single bonds, because they're only sharing 2 electrons, are spaced the furthest apart between 2 atoms, whereas the double bonds and then the triple bonds finally would have the greatest attraction because we have 6 or 4 electrons that are shared between 2 atoms, so we have a greater force of attraction, causing them to be a shorter distance apart from each other. So if you remember that, the potential energy, or the amount of energy that it would take to break apart that bond because they're closer together, is going to be a larger amount. Most of thermochemistry, we're going to be dealing with the energy in the form of heat. So when we look at heat, we always have heat flowing from something hot to something cold. So when we're talking about all these different chemical processes that are taking place, or physical processes, we want to look at the direction of the heat flow. Is it going from the system to the surroundings, or is it going from the surroundings into the system? So you can see in the picture here, I have a lit burner that is heating up some water in a pan, and the heat is being transferred from the burner into the water, and that is going to make the water boil, and in that instance having an endothermic process where it is absorbing the extra heat. So we will start with the first law of thermodynamics, which is basically the law of conservation of energy. Energy is neither created nor destroyed, it's just simply changing forms. In other words, the total energy of the universe is a constant. If the system loses energy, it must be gained by the surroundings and vice versa. So we're always looking at the initial state for the energy versus the final state. So if I have a loss of energy from the surroundings, that would represent this first arrow here where we have the blue arrow. If I have a loss of energy from the surroundings, it's an exothermic process, and that means that my change in energy, delta E, will have a negative value. If we have to have energy gained by the system to make some process take place, that would be referencing the red arrow here, and a positive gain in energy from the surroundings to the system would have the system increasing its overall energy content. When we want to describe the sum of both the kinetic and potential energies that are occurring on all the particles within a system, we describe that as the internal energy, E, for the system. When we have a change in the internal energy for the system, we have an equation, delta E equals Q plus W. Q represents the amount of heat energy, so we will focus mainly on that in this course. The W represents work. Now, when we're talking about this, the work, it must be for gaseous systems. And we'll talk about the equation that we have for work and how that relates to the delta E in just a moment. But it's very simple. You just take your amount of heat energy, add it to the amount of work that's done either on or by the system, and that will tell you what your delta E is for a particular process. Please remember, when we're looking at the internal energy, delta E is representing the final energy position for the system minus the initial energy position. The sign that we have is always reflecting the system's point of view, but please remember that whatever the change in energy is for the system, it will be the negative change in energy for the surroundings. When we are discussing the heat component, again, Q, if it is an endothermic process, that means I'm absorbing energy, so therefore the amount of Q would be positive. If I have an exothermic process, because we're giving away energy, then Q would be negative for the system. When we look at the work portion of our internal energy, work is defined again as force times distance, but in terms of a gaseous system, we can relate it to the pressure times the change in volume. So if you think about volume, where we have a length times width times height, if we're talking about a cylinder, we have the area of the cylinder times the change in height equaling the volume. So your P is your pressure, the A is your area, delta H is the distance that the piston is moving, and delta V is the overall change in volume. If you have a negative amount of work, then the system is doing work on the surroundings. It's releasing energy, and as a result of that, you would end up having a positive delta V. So work is pushing out, so you have the work being done on the surroundings. It is changing the volume in a positive, so I have the negative P times delta V. Delta V is positive, so I would have the work being a negative amount. If my work is positive, then that means that the system is getting work done on it by the surroundings. So it's absorbing energy into it, and I would have a smaller area. So now my delta V, again, final minus initial, my delta V would be a negative number. Negative P times a negative delta V gives me an overall positive W for that scenario. So when we're looking at the different signs for each of these different components, if we're looking at Q, the heat energy, if it has a positive sign, then that means that the system is gaining heat. If it has a negative sign, then the system is losing heat. For W, if I have a positive W, that means that work is being done on the system. So again, getting smaller for the volume. If it's a negative, then that means that work is being done by the system, and so the volume will be getting larger. For delta E, if I have a positive delta E, then that means that I have a net gain of energy by the system, and if I have a negative sign for delta E, that means that I have a net loss of energy by the system. When we have a constant pressure environment, we will focus solely on the change in enthalpy to represent the change in internal energies. At a constant pressure, what we're looking at is that the work equaling the negative pressure times the change in volume. If the pressure does not change, then I will not have any change in volume on the system, and therefore the W would be equal to 0. So when I look at the delta E, then it would just be equal to Q, because Q plus 0 would just be Q. So when we're looking at the heat energy, again, that is a state function we define as delta H for enthalpy. So we're only focusing on the final and the initial states. For the reaction, the path that it takes is independent of the final and the initial values. Enthalpy is an extensive property, which means that it depends on the amount of matter that's present. So you will see your enthalpy values listed typically in terms of kilojoules per mole. However, that can change with the number of moles of the substance that's present within the chemical reaction. The sign for delta H for a reaction in the forward direction is always equal to in magnitude, but opposite in sign to the delta H for the reverse reaction. So you always, and we discussed this back when we did Le Chatelier's principle for equilibrium, the sign is always just the opposite because it's showing us the opposite direction of heat flow. If in the forward direction it's absorbing energy, then that means that it's a positive for delta H. And if we look at the reverse direction, it's the same magnitude, but it would just be releasing energy instead. So it would be a negative sign for delta H. And then finally, delta H for the reaction depends on the state of the products and the state of the reactants. So if you just think about the fact that it would require a certain amount of energy to convert a liquid into the gaseous phase, they're going to have different delta H heat energy contents as a result. When in the lab, we use a process called calorimetry to determine the amount of energy that is flowing through the system. Since we cannot know the exact enthalpy of the reactants and the products, we measure the delta H through this calorimetry process, which is just a measurement of heat flow. You can see in here we have a thermometer, we have a glass stir, a cork stopper, could just be like a styrofoam lid. You have two styrofoam cups that are nestled together, and then you have the reaction mixture in the solution. This is typically done for chemical reactions that are in the aqueous state, and you can measure the change in temperature of the water, which would represent your surroundings, and then you know that the amount of energy either absorbed or released by the surroundings will be equal to the amount of energy that is either given off or absorbed by the system. So one of the biggest places that we have error in our reactions is in calorimetry. So if you look at this diagram, you'll notice that there are two styrofoam cups that are nestled together. So think for just a moment and come up with a reason why you think the two styrofoam cups are used instead of just one. Pause the video, think about it, and then we'll come up with our answers. So as you look at this, you have a couple of different places where energy could be lost to the system. So by doubling up the amount of insulation, i.e. the styrofoam, you're providing an extra layer of protection that does not allow energy to enter or leave the system. However, when we're talking about the error that comes in play with these types of reactions, we have to think about where else we could be losing or gaining the heat. And so when we look at this, you're going to have a certain amount that will be lost to the calorimeter itself. And you can just kind of easily visualize that anytime that you go to, say, Starbucks or Dunkin' Donuts, McDonald's, and you get a coffee. You'll notice that when you get that coffee, the cup will feel hot. So we know that energy is being transferred through the cup. But again, because it's an insulator, it's not allowing as much heat to pass through it. But you also have a couple other objects that are inside. You have the glass thermometer and you have the glass stirring rod. You have air that's above the reaction there in solution, and you have the cork stopper. So all four of those could, in theory, absorb some of the extra energy that's involved in the reaction. So when we do these reactions, we can come up with a calorimeter constant, which we can measure to see how much energy is actually being absorbed per degree Celsius change in the water temperature. We can measure the ability to absorb heat from a substance by looking at either the heat capacity or the specific heat capacity. When we talk about the heat capacity, it's just how much energy is required to raise a certain amount of material by 1 degree Celsius. When we look at the specific heat, that term specific means that we're focusing on 1 gram of the substance instead of just any amount of the substance. And so we'd see how much energy is required to raise 1 gram of a substance by 1 degree Celsius. You could also have a third term where we could look at a molar heat capacity. And if you have a molar heat capacity, as I'm sure you can deduce, we're now looking at how much energy is required to raise 1 mole of a substance by 1 degree Celsius. You can do it by Kelvin or degree Celsius because you're just adding 273 to each number. So it's the same thing for the change in temperature. So you have for this a table that's given to you. You have a specific heat constant for a number of different substances here. And again, a couple of relationship points. The larger the specific heat, so I'm just going to put that here, the larger the specific heat for a particular substance, the greater amount of energy it can absorb without changing the temperature. And so these would be better insulators because they're not going to allow the temperature to change very rapidly. If you have a very low specific heat, now those substances are going to be better conductors instead. So typically you'll find your non-metal type of compounds, covalent compounds, they're going to have relatively high specific heats versus your metals, which are going to have very low specific heats because we know metals are good conductors. When we look at a constant pressure calorimetry experiment, because the specific heat of water is well known, 4.184 joules per gram Kelvin or degree Celsius, we can measure delta H for the reaction with this equation, Q equals mc delta T. Again, remember constant pressure, Q is equal to delta H. So the water in these types of situations would represent your surroundings, and then whatever you are having change the temperature of the water would be your system. So we'll just call that either the chemical reaction or it could also be some type of metal or something like that that you've done in labs before, but that would represent the system. So when we're looking at these reactions, we have Q equals MC delta T. So whatever the value is for Q, just say for instance it's a positive, then the system would have the exact same amount, but it would just be a negative value. When we need to be very precise with our measurements, we can use a bomb calorimeter, which is a special sealed device that does not allow energy into or out of the container. So this would be an example of an isolated container where it has the ability to trap both heat and matter in the place. The energy that is required to heat up some container and burn it inside the bomb chamber here will release energy that the water will then absorb, and as the water absorbs it will change the temperature inside, and they can measure the heat content of the system by again measuring the change in the heat content of the water. So you have the same type of scenario taking place. You have a stir in there, you have a thermometer, and then you have some ignition wire, so supplying electricity to the sample to make it combust. We have the little stir in there because we have water surrounding everywhere. We want to make sure that we have a good flow of water to distribute the heat evenly, so that way it's not all built up right around the thermometer and then on the opposite side of the container having colder temperatures that hasn't mixed as well yet. So they have the stir in there to allow us to have a constant temperature throughout the water and allow us to get a more accurate temperature on the inside. So let's now look at a few example problems. The first one that we'll look at is how much heat is needed to warm 250 grams of water, about 1 cup, from 22 degrees Celsius, which is about room temperature, to 98 degrees Celsius near its boiling point. And then part B, what is the molar heat capacity for water? So in part A, we want to use our Q equals MC delta T equation. And as we begin the process, again, I have 250 grams of water. From the table, we know that the specific heat of water is 4.184 joules per gram times degrees Celsius. And then we have a delta T in this case equal to 98 for my TF minus 22 degrees Celsius for my TI. So that's approximately 76 degrees Celsius. When we plug in those numbers, we get approximately 79,000 for our number of joules, and we can divide that by 1,000 and have that equal 79 kilojoules. For part B, for the molar heat capacity for water, again, we are taking the normal C value for water, which is 4.184, and it's joules for 1 gram per degree Celsius. And then for the molar heat capacity, we're trying to see how much energy is going to be required to raise 1 mole of the substance by 1 degree Celsius. So I just simply multiply that times the 18 grams of water found in 1 mole. That way my grams would cancel and I'm left with moles and degrees Celsius in the denominator. So if I multiply those out, you end up with, I believe it's 75.2 joules per mole Kelvin. So for our next problem, we have large beds of rock are used in some solar heated homes to store heat. Assume that the specific heat constant of the rocks is 0.82 joules per gram degree Kelvin, and we're going to calculate the heat absorbed if 50 kilograms of rocks, if their temperature increases by 12 degrees. So as we begin to look at this particular problem, same thing, Q equals MC delta T. So my Q would be equal to 50,000 grams multiplied by the specific heat constant, 0.82 joules per gram Kelvin, And again, remember Kelvin and degrees Celsius is the same thing for the change in temperature. So whether it's in Celsius or Kelvin, you can just interchange them. So I can multiply that times the 12 Kelvin to get the units to cancel. So at this point, when I plug those in, the amount of heat energy would be 492,000 joules. So again, divide that by 1,000 joules, and that would give me 492 kilojoules of heat that would be absorbed. So I'd have a positive value for Q in this case. So as a part B, it asks what temperature change would these rocks undergo if they emitted 450 kilojoules of heat. So now because they are emitting, that would mean that I would have a negative value for Q. So I'm going to take that and place that as a negative 450 joules. And if I do the 50,000 grams once again, times the 0.82 joules per gram Kelvin, and then we have that times the delta T. So 450,000 divided by 50,000, that would be 9, and then divided by 0.82, or negative 9, so I'd have a delta T in this case equal to negative 10.92, or 98, excuse me, that's it, 98 Kelvin, or degrees Celsius. We will now look at a calorimeter experiment where we are neutralizing an acid and a base. So in this, you have a student mixing 50 milliliters of 1 molar hydrochloric acid and 50 milliliters of 1 molar sodium hydroxide in a coffee cup calorimeter. The temperature of the resultant solution increases from 21 degrees to 27.5 degrees Celsius. Calculate the enthalpy change for the reaction in kilojoules per mole HCl, assuming that the calorimeter loses only a negligible quantity of heat, that the total volume of the solution is 100 milliliters, that its density is 1 gram per milliliter, and the specific heat is equal to 4.18 joules per gram Kelvin. So I know there's a lot of moving parts to this problem, but if you just kind of take it in stride, you'll notice here I've set up my chemical reaction, and I would have NaCl and H2O. This one technically is a limiting reactant type of problem because you're given masses for each of your two starting amounts, and that does come into play. However, hopefully you also notice that I have equal volumes of equimolar amounts of the hydrochloric acid and sodium hydroxide. So in this particular instance, I had that wonderful, perfect stoichiometric relationship there, so I don't have any limiting reactants. So I'm going to look at the information from the surroundings, again, in this case, the water. So the surroundings, again, would be the water, whereas the HCl and the NaOH forming the NaCl and the H2O would be your system. So the chemical reaction again would be my system, and so we're going to measure the energy change in the water, and then we know that whatever is increased by the water is going to be released from the from the system. So in this particular instance, the Q for the H2O would be equal to, it tells us that we have 100 milliliters and the density is 1.0 grams. So I know that I have 100 grams total of the water. We have the 4.18 joules per gram Kelvin. I know that's not 4.184, but this could be due to the parts that are dissolved in it. That will change it a little bit. And then my change in temperature, I have 27.5 minus the 21.0. So that's going to be 6.5 degrees Celsius. And it is an increase in temperature, so I know I'll have a positive Q. So if I take 6.5 and I multiply that times 4.18 and times 100, that gives me a total energy change for the water equal to 2717 for my number of joules, So I can divide that by 1000 and I would have 2.717 kilojoules. So if that's the case, then the Q for my reaction or my system would be the negative of that value, so I'd have a negative 2.717 kilojoules. So now we come to the last part. We need to get this in terms of kilojoules per mole for HCl. So this amount of energy was released from, and if we take the 50, if we take the 50 milliliters and we multiply that times the 1.0 molar, so I'm going to divide this by 1,000 milliliters per liter, and so that would tell me that I would end up with 0.050 moles of HCl. So once again, to solve for delta H in terms of the HCl, I would have the negative 2.717 kilojoules, and I would divide that by the 0.05 moles, 0.050 moles. And when we do that, we end up with a value of 54.3 kilojoules that would be released. So I'd have a negative 54.3 kilojoules. Final answer. So we'll do one final problem. So I want you to pause the video and try to work this one out. This should be very similar to the problem that we just did. So go ahead and pause it, work out the problem, and then watch the answer. So in this problem, we have 0.243 grams of magnesium metal combined with enough HCl to make 100 milliliters of solution in a constant pressure calorimeter. The following reaction occurs. Mg plus 2HCl forms MgCl2 plus H2. If the temperature of the solution increases from 23.0 to 34.1 degrees Celsius as a result of this reaction, calculate, the delta H is missing, in kilojoules per mole for magnesium. Assume that the solution has a specific heat of 4.18 joules per gram degree Celsius and a density of 1 gram per milliliter. So the first thing we need to do, just like the last problem, we want to take the information given and solve for the Q of the water, and that again will tell us the negative Q for the reaction. So for the Q of the water, it tells us that we have a total of 100 grams. We have the specific heat constant, 4.18 joules per gram degree Celsius, and we have the change in temperature being 34.1 minus 23.0. So that's going to be 11.1 degrees Celsius. So my Q for the water, when I multiply that out, gives me 4,639.8 for my number of joules. So in this case, again, dividing that by 1,000 to get the joules into kilojoules, that would give me 4.64 kilojoules of energy. For the second part, that's how much energy was absorbed when 0.243 grams of magnesium metal reacted. Now we need to do it in terms of kilojoules per mole. So the second part I need to do is take the 0.243 grams of magnesium, converting it into moles. 1 mole of magnesium is 24.3 grams. And so that tells me that we have 0.01 for my number of moles of magnesium. So I can now at this point take and that should be the negative Q for the system equaling the positive Q for the water. So in this case, because the water absorbed 4.64 kilojoules, I know that the system, the Q for the system, will equal a negative 4.64 kilojoules. And now I can divide that by the 0.010 moles for the magnesium, and I would get a negative 464 kilojoules per mole. All right, so that ends the first of our lecture videos on the thermochemistry. Our next video is going to be focusing on the different ways that we can calculate delta H. You've already learned one here with calorimetry, but we'll focus on stoichiometry, Hess's law. We will look at the calculation of delta H using bond energies as a alternative method to calculating the enthalpy for the reaction. So have a good night, and please work on the practice problems that are on the Teams page. Thank you.